And I'm doing number 1 right out of the book. The function is f of x equals 2x cubed plus 3x squared minus 36x. Now this is a very nice polynomial function, right? Part A of this says find intervals where f is increasing or decreasing. Part B says find local max, local min. And then part C, find intervals, I'm going to say INT, of concavity. And then find inflection points. I'm just going to put IP for inflection points. But local min, local max. Sorry, yeah, thank you. Now, I'm also going to point something out here because this is absolutely critical when we get to 4.5. Does everyone see that with this, what we're about to do, we're going to find local max and local min? On your test, weren't you asked to find absolute max and absolute min? Right, that was 4.1, wasn't it? What's the difference between what's happening here and what was happening in 4.1? There's something very different about the two problems. We have a second derivative here, yes. There's something else, a little more subtle. It's local, not absolute, right? The idea of increasing these, there's something that in this problem I didn't give you. An interval. An interval. See, if you look at a function and you close it off on an interval, it must have an absolute max and an absolute min, right? That's what 4.1 was about. So all we did was we figured out the critical numbers, we found the endpoints, we plugged all those into the function, right? And we just compared them. Here, I give you no interval. So we're looking at the function on its entire domain and saying, hey, where are the high and low points, right? And where do you change concavity? So that's a huge difference. So I'm going to point out here in red, we're doing this on the implied domain. We're not doing it on an interval. Not on closed interval. That's a big deal, as we'll see later. All right, so how do we do part A? How do we find the intervals where the function is increasing and decreasing? Let's find the derivative, right? Okay, so part A, here we go. First thing I'll do is find the derivative. 6x squared plus 6x minus 36. The next thing I'm going to do is find the critical numbers. How do you find the critical numbers? We've done this, haven't we? All you have to ask yourself is two things. Where's the derivative 0? And where's the derivative not exist? Well, what about the does not exist? We don't have to worry about it, right? NA, not applicable. Why? Our derivative is a polynomial. Polynomial functions are defined everywhere. It has no issues. What about setting it to 0? So that's a quadratic equation. I'm just going to factor 6. Well, I'll divide everything by 6. How about that? Divide both sides by 6. And then factor x plus 3x minus 2. So your two answers are -3 and +2. And see, this time we don't have an interval, right? So we don't have to check to say, oh, do those numbers live in that interval? We're going to have to look at both of them. Yes? Did I what? Did I change it? Okay. Any questions up to this point? So I know where the critical numbers are, right? I know the places, these critical numbers right here, at x equals -3, and at x equals 2, my derivative is 0, which means we have a critical number, right? Now, the first derivative test said there it is right there. If the derivative changes from positive to negative at c, then it's a local max. If it changes from negative to positive, then it's a local min. If it doesn't change signs, nothing happens, right? No local max, local min. So watch the way I'm going to do this. Once I get to this point, and this is going to be our standard practice from here on out, I'm going to draw a number line. I'm going to label the 2 points on my number line. Just make sure you get them in order. And I'm going to use that to partition my number line into in this case, in this problem, into 3 separate regions, right? And then I'm going to pick test points. I'm going to pick a test point over here to the left of -3, a test point between -3 and 2, and a test point to the right of 2. So I'm going to pick a test point in each region. Now, the test point you pick can be any point you want as long as it is in that region. So I'll pick -4, I'll pick 0, and I'll pick 3. Is that all right? What am I interested in? What is it about? What am I going to do with these test points? I want to see if my function is going up or down over there, right? But the way to check if it's going up or down is to take those numbers and plug them into the derivative. Because the derivative is what tells you if you go up or down, right? If the derivative is positive, you're going up. If derivative is negative, you're going down. So what I'm going to do is I'm going to take f prime of -4 and figure out what it is. So everyone plug -4 into the first derivative. Remember, the first derivative was 6x squared plus 6x minus 36. So isn't that 6 times -4 squared plus 6 times -4 minus 36? And if you need a calculator, you probably want to get your calculator out because you'll need it for the quiz most likely. You get 36? Anyone else get 36? Yes? All I care about, though, is what? It's positive, right? It's positive. That's the key. Because it's positive, right? What does that tell me my function is doing over there at -4? My function, so watch the way I write this over here. My function is increasing over here. Why is it increasing? Because the derivative over here was positive, right? The derivative being positive means the function's going up over there. Now, what's happening at -3? It's flattening out, right? So what should we check next? What? 0. The derivative at 0. And at 0, it should be an easy computation. It's -36, isn't it? Which is less than 0, which means we have a negative number. If the derivative is negative, what does that tell me about f? Not concave, we're at the first derivative. It's what? Decreasing. So my function went up and then it's coming down, right? And then let's plug in 3 into the derivative. Comes out to be positive? What's the number? What is it? 36 again? It's positive, and therefore, if my derivative is positive, then that means my function is going up over here. So this function goes up, then it comes down, and then it goes back up. It reaches its maximum point where? Where does it reach its max? At what x value? -3, good. Where does it reach its minimum value? At 2. So I can actually answer, I think, parts A and B here at the same time. Right? Part A, where was the function going up? Where was it going down? So let me go back here. I'll put it in blue. For part A, f is going up on what intervals? Where's my function going up? To the left of -3, correct? So how do you say to the left of -3? Less than -3 or -infinity to -3? Right? Interval notation. Is that the only place it's going up? No, it's also going up past 2. And anytime you have 2 intervals, you put a union symbol between them. How's that? And see my notation, F with the up arrow? Is everyone okay? I'm talking about this, F with the up arrow. Is everyone clear that that in this class is going to mean F is increasing? All right. Now, where is F decreasing? On what intervals? -3 to 2. And that's it, right? Now, I'm going to answer part B above this. For part B, where's my local min and where's my local max? So let's talk about local min first. Where does it happen? At x equals 2, right? That's where it happens? That's where I have a local minimum? Remember, my graph is going down, then it has to go up, right? Over here, it was up, then down. So I should have a local minimum of x equals 2, but I would actually like to know what the minimum value is, what that local minimum is. So how would you figure out what the local minimum is? Plug it into the original function to figure out what the value of the function is there. So plug 2 into the original function. I'm getting -44. Anyone else? Okay. So you could, if you want, look at this as a point. The point 2, -44 is your local min. And then what about local max? Where is it happening? -3 is the x value. And then plug that -3 into the function. Anyone get 81? Yeah, 81? Okay. Any questions? No? Sure, sure.